So using the ideal gas law, we could rewrite the average specific heat of our ideal gas as R, the ideal gas constant, times gamma, all over, this is going to be the molecular weight of the gas times gamma minus 1. So we can replace the average specific heat into that velocity expression to find the velocity equal to 2 times R gamma T1, right? We have Cp times T1 gamma minus 1, and then we have 1 minus P2 over P1 to gamma minus 1 over gamma. This whole thing is square rooted. And we have an expression for the velocity. What we can notice here is that the velocity through this system will increase as we decrease P2, right? So looking at this equation might not be immediately obvious, but a consequence here is that if we start decreasing P2, we're going to start increasing the velocity. We can craft this as a mass flow rate rather than a velocity and look at the mass flow rate as a function of P2 over P1. And what we're going to see is that if we take the differential, so if we look at dm dp, P2 that is, there's going to be a critical pressure at which we get no more additional mass flow. So we take dm dot dp, and what we're going to see is that there's a critical pressure at which there's no additional flow. We do this, and I'm going to give you the expression for the critical pressure. It's quite a bit of legwork. There is a decent amount of derivation in the notes, once again, but once we find this critical pressure, right, math and knowledge. Critical pressure, right, is going to equal the tank pressure, the reservoir pressure, times 2 over gamma plus 1 all to gamma over gamma minus 1. This is the pressure at which we get no additional mass flow rate through the throat of the nozzle. And this is important because this is related to the critical velocity. The critical velocity is the speed of sound. It's the maximum velocity at which a pressure wave can fluctuate through that gas. And so the critical velocity is equal to the square root gamma, the ideal gas constant, our reservoir temperature, all over the molecular weight of the gas species. So we see that we cannot exceed the speed of sound in a nozzle. Right? So no matter how much we try, we're not going to be able to surpass the speed of sound in a nozzle. right? This is at the throat of the nozzle, the critical velocity. No matter how much we continue to create a larger pressure difference, right? Our driving force is that pressure, so we can increase that driving force as much as we'd like. Oops. And we will never exceed the speed of sound. That's what this set of equations and the derivation is telling us. But we know we do exceed the speed of sound. So what we need to create is something we call a de Laval nozzle. And oops, I'm running out of paper here. Let me grab another sheet of paper. And so we need to create something that looks a lot like a Venturi meter. So let's draw this in 2D. So what we had was a nozzle. And the throat of the nozzle was where we expected that critical velocity. And we said, well, no matter what, we can't really exceed that critical pressure or critical velocity. So what we need to do is have a diverging section where now, if this is P crit, the critical pressure, we can keep lowering the pressure out here and then start exceeding the speed of sound. We call this Mach greater than 1. If the speed is greater than the critical velocity, then we've exceeded the speed of sound. We don't do that with the nozzle. We have to create this special de Laval nozzle. And this is a shape you've seen. This you've seen, I'll do a really kind of crude rocket ship here. We have a rocket. You've seen these kind of bell-shaped thrusters. Those thrusters are the diverging section of a de Laval nozzle. And so there's a video that we're going to watch on de Laval nozzles to kind of explain this a little further.